So we just briefly talked about how do we identify both atoms and elements and isotopes. The one thing we need is the atomic number, which is the number of protons, and the atomic mass, which was the number of protons and neutrons together. We talked about how the atomic number was the definitive property for identifying an element, but the atomic mass could vary depending on an isotope, depending on which version of that element we're dealing with. So with that in mind, how are we going to deal with elements and atoms that are so small we can't really, the numbers are just like 10 to the negative 28th or so. And that's where we introduce a mass unit that will deal with that, just to kind of simplify the math, called the atomic mass unit, abbreviated AMU. Whenever we're weighing individual atoms, often we're going to give the number as an AMU. We physically define AMU. When you have a mass, you have to have a standard that mass is based on them. Just like a gram has to have a standard gram that we can weigh. 1 gram always weighs this amount. 1 pound always weighs this amount. 1 foot is always this distant. So, well, we've physically defined AMU so that the main isotope of carbon, 1 atom of that, weighs exactly 12 AMU. The atomic mass of carbon is approximately 12, but we've defined the main isotope of carbon as 12 AMU exactly. From that, we use that as our standard, which we weigh every other atom off of. So they may be fractions of an AMU because they're not perfectly 1 or 2. Remember, when we looked at a proton and a neutron, technically they're like 1.007 or 008 AMUs. So a proton and a neutron are slightly heavier than 1. So you can't just like add those 2 numbers together and get the atomic mass. You can't just say like, well, there's 6 protons and 6 neutrons, it's going to be 12. But so you can calculate that by adding the mass of all protons, neutrons, and electrons. But note, AMU is only going to be dealing with individual atoms, the atomic mass. And in reality, we're going to be dealing with millions and trillions of atoms, some of which are going to be isotopes, which have a different weight. And sure, 1 AMU may not mean much in 2 or 3 atoms. But when you're dealing with millions and billions of atoms, 1 AMU more here is going to keep adding up because you're going to get some of the more and more of the isotopes as you have that many atoms, and the weight is going to drift considerably on what you need. So we have to consider what we call the relative atomic weight. The atomic weight, which is the number that is actually presented on the periodic table below an atom. So you notice we said we defined carbon's main isotope as 12. But if you look at the periodic table, carbon is given as 12.01. If you look at, like, say, some atoms like chlorine, we got 35.45. We get some weird numbers in there that are not really close to a whole number, and that's because the atomic weight is a weighted average of all isotopes based on the percent abundance. So if one isotope is in greater abundance, it's going to take up a greater percent of this weighting. So we're going to add them all up. If you have a 35 and a 37 isotope, we're not going to give it 50-50 weighting unless they're 50% of each guy. So we're going to have to treat this with a little bit of math. Now, while this is kind of semi-tricky math, we're not going to do this very often. I said chlorine has 35 and 37. The 35 chlorine has a 75% abundance. The 37 chlorine has a 25% abundance. So if you collected a jar of 20 chlorines, 25% of that would be chlorine 37. So 5 out of those 20 would be 37. The remaining would be 35. So if I wanted to take the average weight of those 20 atoms, I would have to figure out the weighted average, so to account for that. Bromine, there's 79 and bromine 81. Those guys are approximately 51 to 49% abundant. That's as close to 50-50 as you can get. So what we see when we see the atomic mass, the atomic weight of bromine, is the weighted average of each one. One guy is 78.9, which essentially rounds up to 79. The other guy is 80.9, which essentially rounds up to 81. You take the mass times the percent, and you add it to the mass of the other one times its percent, and you get your average weighted mass, your atomic mass, which is 79.9, which essentially rounds up to 80. So bromine is halfway between 79 and 81, which happens to be 80. You're getting a weighted average. Because we'll never really deal with one atom. We'll be dealing with, I said, billions and trillions. So we will need these. So when we use the number from the periodic table in later chapters, we will use this averaged atomic weight, not the atomic mass. Okay, sure. Okay, I just want to make sure. Yeah, okay. Now, when we look at the periodic table, you'll notice it looks very funny. I've heard it described as kind of like a castle kind of situation, where you have like the front two towers, the gates, followed by the inner wall and the keep all the way on the far right, with maybe like a landing strip or a moat below it. But this table works amazing for characterizing elements. We've put this in this way so that we can understand a lot about the nature of elements. You look at that table, you'll eventually be able to tell something about the reactivity, something about the electronic structure, something about the size, something about what type of bonds they make based on just where they are in that table. So elements are going to be arranged in what we call periods, which is our row, and groups, which is our columns. Now, each period will have a certain range of sizes, which will be due to the electron count, but we'll discuss that in a little bit later. And each group is a range based on its reactivity, such as lithium is above sodium, which is above potassium, which is above rubidium, which is above cesium. All those guys will react very similarly. When they form bonds, they will lose one electron to form one bond. As we move down the table, they'll be more reactive, but they'll form the same types of bonds. Just the same way oxygen, which is above sulfur, which is above selenium, which is above tellurium, and polonium, those guys typically will gain 2 electrons and form 2 bonds. There's a reason why fluorine, chlorine, bromine, iodine are all diatomic gases, and that they form similar reactions with each other. Now, where did this table come from? It wasn't like written whole cloth, because all the elements weren't discovered all at once, but rather in certain bursts. We get a new piece of technology, something that's going to be really useful, and suddenly a whole new wash of elements start coming out of the woodwork, because it's like we knew a bunch of them from ancient times, even if we didn't fully understand them. People understood lead and iron, and they could work that into our tools and whatnot. Then we get things like atomic spectroscopy, which allowed us to differentiate different elements and be like, oh, that new rock you dug out of the ground, that's just iron in a different form. Oh, no, that new rock, oh, that rock has a new element that we've never seen before. You've discovered a new element. And in fact, that's kind of how we discovered helium, by using this, turning the spectroscopy up again along the sun. We saw that, oh, besides hydrogen in the sun, there was actually helium. Thus, we have helium is named after the Greek god Helios, one of the sun gods in Greek and Roman mythology. But 1865, 63 out of 118 elements have been discovered. So a decent chunk. A little bit over half, but not that much. And in 1869, two different chemists separately created a similar periodic table. Dmitry Mendeleev in Russia and Lothar Meyer in Germany. I mean, this was prior to the atomic number. If you look at the table, moving from left to right, top to bottom, it goes up numerically. Atomic number 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is what, like neon. 18 is argon, and so on and so forth. But so it's really obvious to know where to put things when you know the atomic number. But we didn't have that then. But we did have we did have the atomic weight, which did help. Because typically, most elements increase in atomic weight as we increase in atomic number. However, that's not always the case. If you look at some of the transition metals, which are the metals in that middle area, that big, wide, long wall area, some of them, the atomic mass, your atomic weight is slightly heavier on the element to the left than it is on the right, but they were still able to put these in the correct order. Also, they're able to expect, predict, and leave some blanks in that table, saying, here's an element we haven't discovered yet, but it will go right there. They knew there's an element we don't have yet. And that's because of the properties. If you have aluminum and phosphorus, but not silicon, and you go, well, this guy, aluminum acts like boron. I know I can put that there. Phosphorus, that acts like nitrogen, but not like carbon. Well, there must be an element that must go in between there. Something that acts closer to carbon than phosphorus or aluminum will. So we know to leave that blank. And that's part of why this was so powerful at the time. In fact, Dmitry Mendeleev was a little bit of a narcissist, and he knew he was so right that it predicted the weights of known elements, of the elements that were going to be discovered. And one of the guys discovered the elements, and the weight didn't match what Mendeleev predicted. He said, "You're wrong. Go back, recheck your numbers. We'll be danged." But the guy did, and found out Mendeleev was right, and that kind of solidified this table is 100%. This table is the real deal, and kind of just led to being a bigger head than he already had. But just the idea like this helps us understand all about this. There's a reason why copper, silver, and gold are right above each other on the periodic table. Those are our metals we use for most of our coins. Those are some of our precious metals there. So we can break this down into there are some individual group names, but the main thing we need to take away is the metal versus non-metal idea here. On the far left, we have alkali metals, and the next one is alkaline earth metals. But needless to say, both of these guys will make bases in water. Alkali is a term for basic. Like alkali batteries are batteries that have a basic active material. So these guys are in a lot of our bases. This center area is all transition metals. Transition metals. We won't deal with them too much because the properties are kind of a little funky. And then we have some of the last little bit of our metals right here: the aluminum, gallium, indium, tin, bismuth, polonium, lead. But all these are fit under the metal category. Over in the far right, we have what's called the non-metals. Those are going to have completely different properties. You can name some of these like, well, the chalcogens. We don't really typically use the term chalcogen anymore, but we do use the term halogen pretty often. Fluorine, chlorine, bromine, iodine are halogen. When we talk about halogenated solvents, we're talking about solvents that contain these. If you have CFCs, chlorofluorocarbons, those things that screw up the ozone layer, those are halogenated gases. We have the noble gases in the far right column. These are so named because of their pretty much lack of reactivity. And the little barrier between metals and nonmetals are metalloids. They're essentially nonmetals that act very similar to metals. Like silicon acts very similar with carbon, that you can make a lot of the same types of bonds, but it conducts electricity really well, which is why we've been making a lot of computer chips out of that, because they can conduct electricity, silicon chips. And of course, down here we have our intertransition metals, often just referred to as lanthanides and actinides. These are mostly radioactive, mostly man-made, and we won't worry about them much at all, because those get even weirder than the transition metals. You may also notice this UUN, UUU, UUB, and whatnot. Those were placeholder names. We have since discovered we've discovered them and named most of those all. This is just an old table, and I have yet to update that. But like, so those include tennessine and what, like niponium. See a lot of man-made elements, but they were just placeholder names until the official committee could decide on them. So this table is actually filled out a lot more. I just kind of leaving it blank for now. While I'm waiting for that, I'm going to start working on the chief. If we can start looking at some of the homework for this. Some of the homework for this will involve oh God. Some of the homework will involve determining proton, electron, neutron count, isotopes like that. But there might be one or two math problems that are like real math problems. Okay. Now, okay, there was one more slide that it jumped right through. Okay. So we'll go back and finish the last slide. I don't like this. Okay. So just a few quick properties of these guys. All metals share a luster or shininess. The metals are typically highly conductive of electricity and highly conductive of heat. And all except for mercury are solid at room temperature. So mercury is the only liquid metal. When we make bonds and we make compounds, which we'll talk about next chapter, these metals will typically be positively charged. Nonmetals are just about the opposite. They're non-lustrous. They're often non-conductive. One of the few exceptions is carbon in the form of graphite. And they exist in all states of matter. They could be gases, they could be liquids, they can be solids, depending on what they are. Iodine is a solid, bromine is a liquid, chlorine, fluorine, oxygen, nitrogen, gases. And when we deal with most compounds, they'll typically be negatively charged, but it'll be dependent on what they're mixed with. And as I said, metalloids have properties between the two. They can make bonds like carbon, but they act as a semiconductor of electricity, like a metal. They'll be able to recognize some of the simple things. We're going to be looking at bonds between metal and non-metal, and next chapter also bonds between two different non-metals, because those are going to be named differently because they have different properties. And so you need to at least be able to recognize what each one is. Let's see. You'll notice that this one is only 13 problems. Whenever I get this loaded up. Only 13 problems. So there's a lot less this second chapter. Of course, this was also a lot shorter chapter and not a whole lot of math. But looking at this. So some of this stuff is like, oh, hey, reminder back on the history thing. So the smallest unit of charge is 1.6 times 10 to the negative 19 coulombs, which is the charge of a single electron. Robert Millikan was able to measure the charge of small droplets, suspending them between a pair of electrical charge plates. What is a possible value of these oil droplets? So what you're looking for is a multiple of 1.6. If one electron is 1.6, two electrons would be 1.6 plus 1.6, or 3.2. If I had three electrons, 1.6 times 3, 4.8. So you're looking at which of these guys are multiples of 1.6. You can have multiple numbers here. So you have to do that and figure that out. Not all of these are correct. Which statement is true about Rutherford continued theory, the plum pudding model? Who actually devised the plum pudding model? Disproved the plum pudding model. Theorized that atoms contain positively charged region called nucleus. A solar system model. So you may have to go back to the book. Keep in mind, you will always have the option to get a hint. You could also click the book, which is going to go blah, blah. You can click right there, and it will go to the portion of the ebook where that's at. So it's like, oof, I can't remember this. I don't have the slides in front of me. You can always go to the ebook and see exactly, open in a new window and see exactly what it says about Rutherford. So don't feel like you have to guess. So this one, you're asked to name which of the proton, neutron, or electron has a positive charge, negative charge, no charge, where they're located. There may be more than one thing in a blank, much lower mass than the other two. So all that's in the notes. Too hard. Chemical symbol. So this one, they just want you to look at the atomic number. So how are you going to do that? There's a link right there to your periodic table. In case you don't have one in front of you, in case you don't have a book, right there, that gives you a link. So if you're not in class, you can't really work that out. Periodic table. Me, I put an app on my phone, but then again, that's me. So carbon 6, you can go krypton. My eyes aren't good enough to see all the way over there, but it's, I think, 36 because it's right after bromine. but I could be wrong. I could be way wrong. But beryllium is right there. 4. Barium is, oh God, I have no even clue. Don't worry about it. Don't worry about it. But it's essentially, what is the atomic chemical symbol that's given? Determine the atomic number. It's literally, you look there, you find the atomic number, which is in the top portion of that element. So identify the missing information. So this one I'll actually work through. A selenium atom has a mass of 79. Determine the number of protons, neutrons, and electrons. So selenium, over there, it's right next to arsenic, right between bromine. Thankfully, since I just determined krypton is 36, bromine must be 35, selenium must be 34. So the number of protons, by definition, has to be 34 because the atomic number is 34. The number of neutrons, if the atomic mass is 79 and the atomic number is 34, then the difference must be 45. And determine if a selenium has blah, blah, blah. And it's a neutral isotope. Because it's neutral, the number of electrons must be equal to the number of protons. Here we go. A neutral isotope has a mass of 30, 65, and 36 neutrons. Identify the element symbol of the isotope and determine the number of protons and electrons. So I'm going to go protons and electrons first. It's neutral with 65 mass number and 36 neutrons. The difference right there is 29. 29. Because it's neutral, there's 29 electrons. So I need to count what's the 29th element in that series. So what is argon is 18, 19, 20 for calcium. And so that means that should be, what, copper? We're going to go with copper. So Cu. Could be wrong. We'll find out. But I think from what I remember, that should be 9 elements over. Okay. Neutral isotope has 45 neutrons and 36 electrons. So once again, 36 electrons, it's neutral, so it must have 36 protons. Mass number would be 45 plus 36. 45 plus 36, 70, 81. 36 puts it at krypton. Now, that's just from what we said earlier. So make sure you scroll down to get all the questions. Make sure you scroll. I'll do just one of these real quick. Using the periodic table, identify the name and symbol of each neutral atom given an atomic number and mass number. So atomic number 36. 36, well, we just did that one. Krypton. So this one, they want us to spell out the whole name and spell it correctly. So if you miss that, that could be a reason why. Now here, they want us to put in the elemental symbol. The subscript should be the atomic number. And the one up top, the superscript, is just the mass number. Just go and delete the question mark and fill that out. And it'll tell me, what I got right, what I got wrong. It has those marked wrong because I left them blank. But those marked right, so you'll see I got 33% of this correct on the first try. But that's only because I filled out 1/3 of all possible blanks. We're kind of out of time. I just want to look at one more. See, protons, neutrons, electrons. Yep. Okay, so there's 2 of this isotopic mass, and then pairing these guys up based on where they're at. So like being able to read the periodic tables and put the properties in. So real quick here, we'll do the silicon. So we're trying to find what's the average atomic mass. Basically, all you have to do in this type of situation is turn your into a percent. So instead of 92.2, you say 0.922297. You multiply each number across. So this number times this divided by 100, essentially to put it into 0.92. This number times this divided by 100. This number times this divided by 100, and you add all of them up. So this product plus this product plus this product will get you your answer. This one's a little bit harder than the previous one because the previous one just has 2 things. You would say this number times this number divided by 100 plus this number times this number divided by 100. And that would give you essentially 35.45 or something close enough to that. So that is essentially what you're doing there. It's not supposed to be super hard, and so notice this one says to at least 4 significant digits. So if your number is, say, 28, you're going to have 28 and 2 decimal points after that, because that would be 1, 2, 3, 4. And this one says 2 digits after the decimal point. 35.45 might actually be good enough. But that is what we got. Sorry that we started off such a mess. And we will start chapter 3 on Monday.